The objective of Lab 5 is to experimentally measure the internal shear force and bending moment in a simply supported beam with a variety of different loading conditions and geometries. To accomplish this, we will use experimental configurations to measure these internal forces in simply supported beams that have been instrumented with strain gauges. The first experimental setup we will use to measure internal forces measures the shear within the beam of the HST9 shear force apparatus shown here. Before we begin measuring the shear within this beam, let's take a few moments to familiarize ourselves of the components. The HST9 shear force apparatus is a simply supported beam that is supported by two supports on either end. These supports, with reaction forces only in the vertical direction, coincide with points A and E in the first problem in the laboratory preparation assignment. As you know from our analytic work in class, to measure the internal force within a beam, we hypothetically make a cut at a specific point and apply equilibrium equations at this point to solve for the internal shear force. The experimental beam that we will use in this lab has physically been cut at the point shown here. Once the beam has been cut, it is composed of two sections that we will refer to as the short beam and the long beam, both shown here. We will measure the shear force in a beam that has three concentrated loads applied to it. To apply these concentrated loads, we will hang weights using the weight hangers shown here. The shear force will be measured at the cut in the beam using the strain gauge that is in a cantilever position and is connected to both the short beam and the long beam shown here. Prior to measuring the shear force, it is extremely important to level both beams before we apply the weight. We will consider this scenario to be zero shear force. The first step in leveling the beam is to position the weight hangers at points B, C, and D, which are 100, 300, and 600 millimeters away from point A, respectively. For ease of measurement, each black tick on the beam is spaced 5 centimeters apart. The second step is to level the short beam section using the spirit level, which is the small yellow level that was provided to you. Position the spirit level onto the short beam section as close to the edge of the cut beam as possible. The short beam is adjusted by adjusting the spring force within the counterbalance section as shown here. Level the short beam by adjusting the thumb screw that's attached to the counterbalance section. Using a top-down view of the spirit level, adjust the force within the spring in the counterbalance section until the short beam is leveled. The next step is to level the long beam using a very similar approach to what we just did in the short beam. Position the spirit level to rest on the edge of the long beam as shown here. This will be positioned right next to the weight hanger that is positioned at point B. To level the long beam, adjust the thumb screw that is attached to the cantilever section of the beam. Again, using a top-down view of the spirit level, adjust the thumb screw until the long beam is leveled. The next step is to tare the strain gauge. Now this has to be done by a course instructor or a TA, so please raise your hand when you're ready for this step. Once zeroed, add weights to the weight hangers that are hung on the beam. You will apply a 5 Newton weight at point B, a 2 Newton weight at point C, and a 10 Newton weight at point D. The magnitude of the weight is indicated on the weight, as shown here on the 10 Newton weight. Once loaded, the beam will significantly deflect. Therefore, repeat steps 2 through 6 to level the loaded beam. Once the loaded beam is leveled, record the strain in the strain gauge by again using a course instructor or a TA. The next portion of the lab will measure the internal bending moment within a simply supported beam. Before we measure the moment, let's again familiarize ourselves with the components of this beam. This beam, which is composed of 80-20 material, is a simply supported beam that is again supported by two supports on either end. These supports, with reaction forces only in the vertical direction, coincide with points A and D in the second problem of your laboratory preparation assignment. The beam has been cut into two pieces at the point shown here, and these two pieces are connected by a strain gauge, shown here. If you think about how you would analytically solve for the bending moment in span BC, you would first make a hypothetical cut between points B and C. You would then draw a free body diagram, as shown here, that includes the internal forces at the cut. The cut is represented by a distance x from point A, and the external forces that we will use in our analysis will be the reaction force at A and the concentrated force F1 applied at point B. We then apply the equations of equilibrium, including all of these forces, both external and internal, to solve for the internal forces. However, as you can imagine, we're not actually going to be physically cutting this beam. And so in order to overcome this obstacle, we're going to be changing the scalar distances d1 and d2, which is where the forces are applied, as well as the span of the beam, length L. And therefore, we're inherently going to be measuring the bending moment in two separate simply supported beams with similar loading conditions that are located at different locations. And these locations are described in Table 2 of your laboratory assignment. In order to measure the internal bending moment in span BC of our experimental setup, the first step here is to adjust the span of the beam, which is the distance between points A and D, to be a distance of 0.625 meters apart. The next step is to apply the loads to the beam. First, apply a concentrated force at point B that will be a distance of 0.2 meters, or d1, from point A. The second loading condition we will use will be a force couple system applied at point C. To experimentally create this force couple system, we will hang a weight from a cantilever beam, as shown here. As you know from our work with equivalent force couple systems in class, if we hang a 0.5 kilogram mass from the end of the cantilever device, an equivalent force couple system is created at point C, which is the end of the cantilever. So therefore, position the cantilever at a distance d2, or 0.585 meters, away from point A. The next step is to position the strain gauge in a position that will measure the bending moment in span BC. Inherently, the measurements that you were given ensure that the strain gauge is measuring the moment in the correct span between points B and C, or where the forces are applied. The final step is to measure the distance x, shown here, which is the distance between point A to where the beam has been cut. And this will be used in the analytic equations for comparisons to what we measure experimentally. Once the beam is in the correct position, record the value in the strain gauge that will be used to calculate the bending moment in the beam. Again, to get the recording from the strain gauge, please seek a course instructor or a TA to get the reading for you. The final portion of the lab is to measure the bending moment in span CD of the beam. To do this, repeat steps 1 through 5 that we just went through, but using the updated values provided in Table 2 of your lab assignment. As you can see when you read the laboratory assignment, the main component here is to compare our experimental internal force readings to our analytic equations that we derived in our pre-lab. Now it will save you a ton of time in lab if you come ready with an Excel spreadsheet with these analytic equations already programmed in.